Hello everyone, in this video I will talk about music generation using neural network and show you an example that I created using PyTorch library with these principles. First, a little background information on why I chose my project. Google created this Doodle in March that allows anyone to write a short piece of music, then their neural net will automatically create a Bach style 4-part chorale for it. I thought this was really cool and hope that I can create something similar on my own. This doodle is based off an awesome neural network created by the Google Magenta team and is called the Coconet, or counterpoint by convolution. In Coconet, they employed orderless NADE to estimate the probability distribution of the other three tracks given one input track. But these are too complex for my small project. Instead, I went all the way down to the basic stuff these neural networks are based upon, and is called a restricted Boltzmann machine, or RBM. An RBM is an undirected network with information passing back and forth between the fully connected visible layer and hidden layer. When it reaches convergence, the values in the visible layer is the generated pattern. A convolutional RBM uses the convolution operation in place of the linear full connection to capture spatial information, which is vital to music generation, because any note is related not only to other notes played at the same time but also to those before and after it. Although RNNs, or recurrent neural networks, are good at handling sequential information, Coconet and many other networks chose to use RBM over RNN because music generation does not happen in sequential or linear format, since the composer may go back and revise some notes every now and then. And to implement this in PyTorch, I used the dataset organized by Boulanger-Lewandowski, which is also what the Google team had used. The neural network takes in a series of 4 tuples converted to 4 channels of 1/2 encoded vectors that represents the pitch played at any given time. The 4 channels are the visible layer. They would then convolve with kernels covering all pitch range into 2048 channels of feature maps. That's the hidden layer. And the feature maps will then be deconvolved, and after a few iterations, the output is given in 4 channels of probability distribution heat map. To train the neural network, I erase 3 channels in the inputs and correct the 1 channel kept in each iteration. After convergence, the loss is calculated as the mean squared error between the ground truth and the generated pattern. Parameters are updated using an Adam optimizer. And the training efficiency, as you can see, is not very high, but the neural network certainly learned something. Over 100 epochs, and the training loss and test loss are very close. When I look at the actual results, I realized the only thing I learned was to not mess with the input channel. I think this is because the neural network has to base its predictions on something solid apart from the total randomness I was giving it. The Magenta team has a way to estimate the confidence level for each note generated and decide whether to keep that or rewrite it in the next iteration. There are also better stochastic methods, optimization, and regularization algorithms described in all these papers, which I did not have time to implement. I will try to improve my code with these features in the future, and you can find links to all the references I used in the project below the video. Thanks for watching.